In this lecture, we will cover the Thevenin's theorem. Assume we have a circuit which is divided into two parts, circuit A and circuit B. Thevenin theorem states that replacing the circuit A with the Thevenin equivalent does not change the voltage and current of any elements in circuit B. The Thevenin equivalent circuit consists of a voltage source, V open circuit, and a resistor which is called the Thevenin resistor. There is one more condition. If the circuit contains a dependent source, both parts of the dependent source must be either in A or B for the Thevenin theorem to work. In order to find the Thevenin equivalent circuit of circuit A, we need to find V open circuit, I short circuit, or the Thevenin resistance of circuit A. Actually, it is enough for us to find 2 out of the 3 because, for instance, we can find I short circuit as V open circuit divided by Thevenin resistance. There are 2 ways to find the Thevenin resistance. We create firstly circuit A star. We replace all the independent voltage sources by short circuit and all the independent current circuits by open circuits. And we find the resistance by replacing series and parallel resistors by equivalent resistors, or we can alternatively do this by using this relationship. V open circuit is equal to RT times I short circuit. So in this exercise, we need to find the Thevenin equivalent circuit as seen from the ports A and B. In order to do this, we need to first calculate the plus minus V open circuit voltage. Here I have V open circuit, and obviously since this is an open circuit, the current passing this way will be equal to 0. Then there will be no voltage drop over this 4 ohm resistor, and I will simply have V open circuit here as well. Accordingly, V open circuit will be, I will disregard this 4 ohm resistor, 50 times 20 ohms divided by 20 ohms plus 5 ohms. I followed the voltage divider rule here, and it will be equal to 40 volts. I found the V open circuit. I can continue finding the Thevenin equivalent circuit by finding the I short circuit. Let's do it that way. Plus minus. Now I short circuited the ports A and B, and I short circuit will be the current passing through this 4 ohm resistor. Here I have 50 volts. And let us assume that here I have VC. I need to write the Kirchhoff's current law for the node VC. VC minus 50 divided by 5 plus VC divided by 20 plus VC divided by 4 is equal to 0. From here I get 4VC minus 200 plus VC plus 5VC is equal to 0. From here I get 10VC is equal to 200 and VC is equal to 20 volts. And I short circuit accordingly will become VC over 4 ohms, and this is equal to 20 over 4, 5 amperes. I short circuit is 5 amperes. Now our Thevenin is equal to V open circuit divided by I short circuit, and this will be 40 volts divided by 5 amperes, and it will be equal to 8 ohms. So as a result, my equivalent circuit will be plus minus VOC, which is equal to 40 volts. The R Thevenin, which is equal to 8 ohms. And here are the ports A and B. So I found the Thevenin equivalent circuit. Let's find the Thevenin equivalent circuit using another way. Remember, in the previous slide, I found VOC is equal to 40 volts. I will now assume that we don't have this 50 volt voltage source, and I will reduce this circuit to a resistor network. So here I will have 5 ohms. In parallel to that, I have 20 ohms. I had the 5 ohms here on the upper part. I took it to the left part, but that is an operation which I can do. Here I have 4 ohms. And here are the output ports A and B. Obviously, since these 5 ohm and 20 ohm are connected to the same nodes on the upper and below part, let's highlight them. They are in parallel. So let me calculate 5 ohm in parallel with 20 ohms, which is equal to 1 over 5 plus 1 over 20, which will be 100 divided by 25, accordingly 4 ohms. So this is my first step. So I reduced my circuit to this. 4 ohm resistor, another 4 ohm resistor, and the output ports A and B, through which I want to find the equivalent resistance. Now I observe that these two resistors are in series with each other, and therefore I can simply write the equivalent Thevenin resistance is equal to 4 ohms plus 4 ohms and equal to 8 ohms. So basically, this time I found the equivalent Thevenin resistance by doing the reduction of the resistors, and I found 8 ohms again. Therefore, this is another way of finding the equivalent circuit. Alright, let's start with finding the V open circuit, plus minus V open circuit. Since no current will flow through this 4 ohms, I can say that V open circuit is equal to the potential here as well. And let us write the Kirchhoff's current law for this circuit. V open circuit minus 10 divided by 10. This is the current going this way. Then V open circuit divided by 40. Then 2 amperes is going out this way. There is no current going out that way, is equal to 0. So from here I can write V open circuit minus 40 plus V open circuit plus 80 is equal to 0. So from here I get 5 V open circuit is equal to minus 40, and V open circuit is equal to minus 8 volts. So firstly I found the open circuit voltage of the circuit, and the Thevenin open circuit voltage is a negative voltage. Yes, this can happen. Let's then find the Thevenin equivalent resistance by short circuiting the voltage sources and open circuiting the current sources. The equivalent circuit, the resistor network, will be 10 ohms in parallel with 40 ohms, and here we will have a 4 ohm resistor. As you can see, I don't have the current source here, and the voltage source is short circuited. So 40 in parallel with 10 will give the equivalent resistance of 8 ohms. Then this circuit will be simply reduced to 8 ohms, 4 ohms, and the output ports A and B. And since 4 and 8 are in parallel, our equivalent is equal to 12 ohms. My V open circuit is minus 8 volts. Our equivalent is 12 ohms. Accordingly, I can write minus plus 8 volts. And here 12 ohms for my Thevenin equivalent circuit. So here I have my Thevenin equivalent circuit, and I finished solving this example as well. Okay, this is very easy. I will now solve this very quickly and you will understand it. V open circuit will be equal to 2 volts. I did not do this without doing any algebraic manipulations because I know no current will be passing this way. I have the open circuit through these 2 ports, and I can assume that the whole circuit is actually 3 volts connected to a 3 ohm resistor and 6 ohm resistor, and I will do a voltage division in which 1/3 of the voltage will be dropping over this 3 ohms and 2/3 will be dropping over the 6 ohms. Accordingly, I wrote by just looking at the circuit 2 volts. Now I will reduce this circuit. For that I will draw 3 ohms, 6 ohms, and here I have 6 ohms again. Around these times, you need to have the ability to quickly recall what are the equivalent resistor values for some of the parallel resistances. For instance, if we have 3 ohms and in parallel with 6 ohms, the result is 2 ohms, and 2 ohms in series with 6 will give the R Thevenin as equal to 8 ohms. So the value of the V open circuit is 2 volts, value of the R Thevenin is 8, and I found the Thevenin equivalent circuit for this circuit. Alright, we have a circuit here with a dependent source that might complicate things a bit, but actually not. We will follow the standard procedures. Here, let's find V open circuit first. I define it here. I know no current is passing here. Therefore, the value of the voltage between the node C and the reference node is equal to VOC. But let's see, I have a current I passing this way. This current should be passing over here and here as well. Indeed, this is the current around this loop. So let's write the Kirchhoff's voltage law then. 6 times I minus 2I plus 6 times I is equal to 20. From here I calculate I as 2 amperes and VOC will be simply 6 ohms times I, which is equal to 6 ohms times 2 amperes, and this is equal to 12 volts. I found the V open circuit voltage. Alright, in the previous slide we found V open circuit is equal to 12 volts. Now I want to find the I short circuit through this ports A and B. I can probably solve this using the node voltage analysis. I will define this as VC and I will define this node as VB. And I see VC minus VB is equal to 2 times I. And I see that I is equal to VC over 6. So accordingly, VC minus VB is equal to VC over 3. And from here, I get 2 over 3 VC is equal to VB. Okay, this is one of the equations I found, so I will use it somewhere in the future. Now I see we have here a dependent source, and I can create a supernode around this. What will I have? current going out this way, current going out this way, and current going out this way. So let's write VB minus 20 divided by 6 plus VC divided by 6 plus VC divided by 10 is equal to 0. I can write this further as 5VB minus 100 plus 5VC plus 3VC is equal to 0. Let's simplify this further. 5VB plus 8VC is equal to 100. I can go to 1 and take this, and wherever I see VB, I write 2 over 3 VC. So I end up having here 10 over 3 VC plus 8 VC is equal to 100. So I have 10 over 3 is 3.33. 11.33 VC is equal to 100, and VC is equal to, I need a calculator, 8.82 amperes. If I know VC, I short circuit is VC divided by 10, and this will be equal to, here this is not an amperes, this is volts. I made a mistake. 8.82 volts divided by 10 ohms, and it will be 0.882 amperes. So this is how I find the I short circuit. In order to find Thevenin resistance RT, I need to divide V open circuit by I short circuit. 12 volts divided by 0.882 amperes, and this will be equal to, I need my calculator, approximately 13.6 ohms. Accordingly, the Thevenin equivalent circuit is 13.6 ohm Thevenin resistance and plus minus 12 volts voltage source. Alright, I need to find V open circuit. How will I do that? I will write plus minus V open circuit here. I know no current is flowing because here I have an open circuit. So here I will have V open circuit. But V open circuit, due to this current dependent voltage source, will be equal to 2 times IA. Nice. Now, actually, this whole circuit consists of one single loop over which the current IA is flowing. So let us try to write the Kirchhoff's voltage law for that loop. Minus 2 times IA plus 6 times IA plus 12 is equal to 0. From here, I get IA is equal to minus 3 amps. And accordingly, V open circuit will be 2 times IA and is equal to minus 6 volts. Alright, I think I found this rather easily. Now I need to start solving the second part. I will redraw the circuit such that I don't get confused. Here I have the I short circuit flowing. Here I have my dependent source again. And I have here the current IA flowing. Since this current will also flow over this and over this, so I know here IA is flowing as well. So the value of this voltage source is 2IA. So in other words, here at this port, assuming this is my reference port, I will have the value of 2IA as well. Now, I can find the value of this IA as 2IA minus 12 divided by 6, and accordingly 6IA is equal to 2IA minus 12. From here I find IA is equal to, if I am not wrong, minus 3 amps. But I am interested in finding I short circuit. I short circuit will be equal to 2 times IA divided by 3. 2 times divided by 3, and it will be equal to minus 2 amperes. I have V open circuit, I have I short circuit. Accordingly, our Thevenin will be equal to V open circuit divided by I short circuit, which is equal to minus 6 volts divided by minus 2 amperes, and is equal to 3 ohms.